Well, hello and welcome everyone to Insight with political tours and beyond the headlines. As world leaders gather in Glasgow next week for the COP26 summit on global warming, we're going to take a look at one region where global warming is already having a dramatic effect and ask what lessons it has for us. We're joined by Michael Bevis, Professor of Geodynamics at the School of Earth Sciences at Ohio State University. Michael led a team of researchers that published a paper showing a rapid acceleration of the Greenland ice melt. And it's that we're going to be looking at in some detail now. Hello and welcome, Michael.
Hi, good to be here.
Thank you very much for joining us. Just to start with, we're going to delve into this in some detail. It's going to be fascinating and also quite alarming to look at this in some detail. Can you just explain what your work is generally? You're actually a geophysicist, and so your area of focus is to look at, we'll use technology to study the Earth's surface.
Yeah, I'm a geophysicist, and my sort of sub-branch is called geodesy, which is where we use things like GPS satellites to measure the Earth so precisely that we can watch it deform. So, for example, we can measure the position of a GPS station to a millimeter or two, and then just watch it move over periods of years, and then try to unravel the various causes, usually overlapping causes, that explain that movement. So it might be plate motion, it could be earthquakes, it could be changes in hydrological cycle, ice losses in polar areas. So there are a lot of different things happening, and the game is to try to unravel them and relate cause and effect.
Got it. I mean, I was before we get to Greenland, you're looking at sort of tectonic plate shifts and movements up to as much as 25 centimeters a year underneath the Pacific.
Right. This is in the Tonga area. So that was one of my first big GPS projects, was to measure the positions of islands either side of the Tonga Trench, and then do that every year or two and watch them get closer and closer. And then we could infer that, the plate motions across that trench were 25 centimeters a year, which is the fastest plate motions on Earth. And that's sort of an example, like in that place, plate motion is the dominant signal. But in other places, for example, in Greenland, climate change is the dominant signal.
Yes, no, absolutely. Well, that's my next question, really. How did you move from that to working in Greenland? What took you to Greenland?
Well, I started working in the South Pacific to measure plate motions in Tonga area and in the New Hebrides. And then I started to work in South America, and I was looking at the deformation of the Andes, watching the Andes actually grow in some places and looking at the earthquake deformation cycle. And I started to pick up hydrological signals, which I thought was strange. I had a station in the center of the Amazon basin in a city called Manaus. And if you just looked at the vertical coordinate of the station, it looked like kind of a sine wave. It was going up and down every year. And it was going up and down by about 2.5 inches. And I was thinking, what on earth is going on with this GPS station? And it's right next to the Amazon River and also the Rio Negro, which is at the confluence of those rivers. And we looked at the river level and we saw it was anti-correlated. So when the river level rose, the river would increase from being 2 kilometers wide to being 20 kilometers wide. And just the weight of that water deforms the Earth because the Earth's inelastic. So if you put a big weight on an elastic spring, it will be compressed. And if you take that weight off, it will recover. And so that was what was happening in Manaus. It was just, we were weighing the Amazon River, essentially, with the GPS station. And that sort of got me thinking, well, what else can we measure? Maybe that we should try to use this for climate change as well and start measuring the ice. In fact, someone had mentioned measuring, Brad Hager had mentioned like 10, 15 years earlier, hey, maybe we could measure the weight of the ice changing with GPS. But at that point, it really wasn't viable. But then it was, the technology could run on its own. You could build stations that would just sit out there, hundreds of miles from the nearest person with solar panels and batteries, with satellite comms, and you could run these things all year round. And so around 2006, I proposed to build this network called GNet, Greenland GPS network. And we built it in 2007, 2008. And then it's been running ever since. And that was the first large GPS network that was built specifically to study climate change.
And obviously that shows you, I mean, the report that you produced on the ice melt was in 2019. So that really shows that you're building up an area of knowledge over quite a bit of, that's over sort of 12 years time. You chose an area in the southwest of Greenland. Many researchers had really been looking at the key glacial melt or key glaciers, and the southwest hadn't been an area of interest. Why did you choose that area?
Well, so we actually built a network that covered the entire circumference of Greenland. So it's a giant ice sheet, and then there's a strip of coast, and sometimes that strip of coast where you've got rock and permafrost is only 10 kilometers wide. In other places, it's significantly wider. So we built sort of all the way around, but we were sort of expecting the big signals in the southeast and the northwest, because that's where most of the major outlet glaciers are. So one of the ways you can get a net loss of ice is for the outlet glaciers to speed up. So they're producing icebergs at a higher rate, and that draws down the ice sheet. So we were sort of expecting in the southeast and the northwest to see the biggest signals. But eventually what we realized was the biggest acceleration was actually in the southwest. And that's a place without very many glaciers. So it seemed really odd at first. And then we realized, well, it's not the acceleration of the glacier outpouring icebergs into the ocean. It's actually the melting of the ice sheet and the ice leaving as river water. So this is what you call surface mass balance. In an ice sheet, there's sort of two main modes of losing ice. One is dynamic mass balance, that is the glacier process speeding up. And the other is surface mass balance, which is just the difference between sort of precipitation in and melt water out.
Okay,
so
we're going to delve into a bit of, because there are lots of things going on here. I mean, I know nothing about this. You spent years studying it. So it's a bit of I'm in at the deep end here. But can we, I'm just trying to think of, there are multiple things influencing the ice there. And you just talked about that. There's background temperature, which has obviously been increasing over the last, several decades. But there are other elements going on as well. And there are changes, obviously there's seasonal change in temperatures, but there's a cyclical change in temperature as well. Can you talk a bit about that in terms of the balance weather patterns over periods of years?
Yeah, there's basically two big drivers. One is the air getting warmer or changes in the amount of sunlight. So that's sort of like atmospheric forcing. And the other is the ocean getting warmer, because the ocean getting warmer is one of the things that's helping to speed up the glaciers. They are basically being worn away by warmer water, right? And so the production of icebergs increases. So you've got both global warming in the usual sense of the air and global warming of the oceans, and they're both having an impact. And those warmings come in sort of three flavors. The long-term trend, this is what we think of as global warming, right? It's getting warmer and warmer and warmer over decades, and it's going to continue to do so. Then there are natural cycles superimposed on that. So you've got the sort of like the North Atlantic oscillation is a natural cycle. El Nino is a natural cycle. So you have longer term trends and cycles, and they're affecting both the atmosphere and the ocean. Okay. So in terms of the ocean, that's the warming of the ocean tends to speed up the glacial loss, whereas the warming of the atmosphere tends to speed up via melting.
Got it. We're going to talk briefly about that North Atlantic oscillation. Just tell it, there was one description I read about it as being like a seesaw of pressure between the Azores and the Arctic, right. And where that pressure is down. Well, you explain it.
Well, it's a seesaw in pressure between the Azores and the Greenland area, and then there's a positive phase and a negative phase. So, in the case of the negative phase, for example, what happens is you tend to end up with a high pressure system sitting over southern Greenland, over a large part of Greenland, in fact. And high pressure systems mean clear skies, fewer clouds. So that increases the amount of sunlight hitting the ice, which when that happens in summer, it'll tend to melt it. The other thing that it does is it draws warm air from the south up the west coast of Greenland, from the very far south to the, all the way up to the west coast. And so that's also bringing, more heat into the ice sheet. So the combination of the clear skies and more solar radiation, and then literally warm air being pulled up the west coast, accelerates the melting in summer. The funny thing is that the effect's not really uniform. If you think of it like this, think about, you've got, say, 3 degrees of warming happen over a certain period of time. If that warming takes you from -5 to -3, its impact's not that big because it's still under the melting point, right? But if it goes from -2 to +1, that's a much bigger impact. It's the same amount of warming, but the impact's different. So you can have these trends that go on for ages, and then all of a sudden they start to have a big impact.
It's the consistency of that temperature, bobbling above zero, which is the ruinous aspect of it.
Right. So what, there's the temperature change, and then there's the vulnerability of the ice sheet to that change. So that if the ice sheet's sort of, -10 degrees, having it go to -9 degrees is really not going to do anything. Right. But if it goes from -2 degrees to +2 degrees, it's going to melt like crazy.
Yeah.
So and similar stuff happens in the ocean, that, if it gets slightly warmer, but it's still really, really cold, it will have a smaller effect. But if it warms up a lot, it's going to have much more impact on the calving process and then the outflow of the icebergs.
So if you've got rainwater going on, I was reading this earlier, and there's one of the articles about your process, about your paper. And can you say what the melt albedo positive feedback is? I mean, that's a real mouthful, but it's concerning. It's basically about rain on glaciers.
Yeah, I mean, there's a range of albedo effects. I mean, the most famous one is in the Arctic Ocean, where we're losing summertime ice, right? So it used to be that there would be quite a lot of the Arctic Ocean still had ice in summertime, but now less and less of it does. So when you replace floating ice with just seawater with no ice there, it changes from white to something that's a lot closer to black, right? And so the sunlight would, in the old days, would come down into the Arctic and bounce off of the floating ice. But now when it's coming down, there is no ice. It's seeing dark seawater. That radiation is absorbed instead. And so warming led to loss of the sea ice, but the loss of the sea ice led to additional warming. That's a positive feedback. And there are things like that happening too. Like you can melt more ice, and then you can concentrate soot, for example, locally. So the ice becomes blacker because, you melted off the ice, but the soot gets more concentrated at the surface. But now that the ice is darker, it'll be more efficient at absorbing sunlight. And that is another positive feedback.
Right. Okay. In a moment, we're going to talk about tipping points, but I'm just going to bring up a couple of graphs, well, not graphs, just things to illustrate what we're looking at. So briefly, we've got Greenland here, and the area you were talking about is the southwest there. So we're not going to. We'll move on from that one. To what are we looking at here, then, Michael?
Well, on the left, this is a picture of Greenland, where the gray is the rock, right? So that's where there's no ice, and where the colors are is the ice, and I've color coded it by height. So you can see that in the interior of the ice sheet, it's more than 3 kilometers high, right? And that makes it very cold, which is why I chose blue for that color. Whereas the red colors represent ice that's much lower down. And of course, there's 2 ways of getting warmer: either go south or go down. And so most of the melting tends to be in those red and yellow areas because they're warmer, than places higher up. The picture on the right is showing you the acceleration in ice loss we tracked from about 2003 to early 2013. And strangely, that center of this 10-year acceleration was in the southwest, where there are very few outlet glaciers. And so this meant that this was essentially an acceleration in summertime melting. And it was correlated with this natural cycle called the North Atlantic Oscillation. So the North Atlantic Oscillation, when it goes negative, draws warm air up the west coast, and it makes for more clear skies and therefore more sunlight. And because that North Atlantic Oscillation, it's pushing the system in the direction of warming, right? So you've got this slow progressive warming. And then when the North Atlantic Oscillation gets into a strongly negative mode, it gives additional warming. It's a double whammy, right? And so that double whammy was building up over a period of about 7 years and causing an acceleration in ice loss. And then in 2013, suddenly, North Atlantic Oscillation switched to the opposite phase, and the ice loss just stopped. So we had watched ice loss increase from, between 2003 and 2013, the Greenland ice sheet lost about 2,500 billion tons of ice. And then suddenly, starting in the middle of 2013, it lost almost no ice for a year, no net loss. And that was because this oscillation had flipped from helping the warming to fighting the warming.
Let's just come to the next slide, because I think we've got a better illustration of some of those temperature differences here. Michael, you haven't seen this, so this is essentially showing air temperature and sea level pressure from this summer, but this is also part of this pattern.
Right. There are natural patterns, there are natural cycles happening. There are cycles in pressure, and what they tend to affect is wind, and also they tend to affect cloud cover. But there are also cycles directly in the temperature of the sea. So for example, there's one called the Atlantic multi-decadal oscillation. That's an oscillation too. It has a time period of has a characteristic time scale of about 67 years. And it modulates things. So for example, in the late 80s and 90s, the AMO was helping global warming of the ocean. So it was making the glaciers run even faster. Right now, the Atlantic multi-decadal oscillation, the AMO, is actually going in the opposite direction. So now it's beginning to fight ocean warming. So it's sort of suppressing the speed up of the glaciers. But then in another 50 years, it's going to be helping again.
Right.
So you have this sort of interplay between, a progressive trend, this steady warming of the ocean, steady warming of the air, and then these oscillations, which can either help, making a double whammy, or they can hinder. They can sort of try to fight it. But in the long run, they go nowhere, right? Okay. So what they do is temporary. That's the nature of the cycle.
So in the moment, we're going to get towards a discussion on the word tipping point, and we're going to look at it and applying to various things. I'll come on to that in a second. But in terms of global warming and this ice melt, because of the amount of carbon released into the atmosphere, and let's say even minimal projected temperature increases, this is an irreversible process, at least for the next century or so. Is that right?
Yeah, I think that I made the case in our last paper that it's unimaginable that we're going to go back to the behavior of the last century. That the air now is so warm that melting is this like new mode of melting that occurred, sort of started around 2002, is not going to reverse. So we're going to look at more and more melting, and that's going to cause an acceleration in sea level rise. In fact, that period, 2003 to 2013, where there was a tremendous acceleration in melting, during that period, sea level was accelerating too, and it's possible to show that the accelerated melting of Greenland was in large part responsible for the acceleration in sea level rise. And it was a big.
We're talking global sea rise.
Yeah, global sea level rise.
Let's go on to the next slide here, and this is where we get into this might look pretty confusing, but this is where we're going to start talking about tipping points. And so we just said at the moment that the warming that is causing the ice melt in Greenland is irreversible. That's not going to change. The comparison here is with the El Nino and La Nina effect in the Pacific. And this is, so let's just describe this, and then we'll get onto the idea of tipping points. To the point, I think, the point about tipping points is that if you have multiple tipping points, there is an acceleration in global warming from which you cannot pull back. And we're in this phase, I think you're suggesting, and other scientists are suggesting, where we can do things that prevent us from reaching this tipping point. So that's why the use of the word tipping point is actually so important, because the implication is that you can do nothing about global warming. What are we looking at here?
Well, let me first say that there's sort of two visions of tipping points. One are there's a sudden onset of something that won't go away, right? And then there's a second notion, which is basically a runaway tipping point. That's where it just takes off and it ramps up towards disaster, sort of like a chain reaction in an atomic bomb. Most tipping points are not runaway tipping points that will self-reinforce indefinitely and cause, massive disaster. This is a pretty bad tipping point though. So this is a cartoon that you're seeing on the screen if you're watching, and I'll try to describe it. And it's showing the temperature of the tropical ocean, sort of mean tropical sea surface temperature. It is a cartoon because there's a lot of different ways to define that, and I just chose one, right? Then for the sake of argument.
When you use the word cartoon, you're using it in the traditional sense, in the way of an illustration stretched out on
right.
Yeah.
So there's this curve and it's wiggling up and down, and that's sea surface temperature, and that's the El Nino La Nina. During the La Nina phase, basically heat is being stuffed into the ocean, and a lot of it into the deep ocean. And during an El Nino event, it gets dumped into the shallow ocean and also into the atmosphere. So every time there's an El Nino event, the shallow tropical ocean gets warmer. And this is now driving the destruction of coral reefs. There is a phenomenon, probably most of you have heard about it, called coral bleaching. It was around in the 60s and 70s, but it was highly localized and often associated with strange, unnormal things like extreme pollution. But then in the 70s and 80s, people noticed that, hey, these coral bleaching events are now affecting large regions, and they're occurring during El Nino. So what's happening is the El Nino is making the water so warm that the coral is basically dying. And so you end up with a reef that's just, a white mess, nothing alive, no fish. It's horror show. But they were regional events, and all of the oceanographers were satisfied. Yes, these events are being driven by El Nino. Then in 1997, 98, we had the first huge El Nino in the modern era, when we can measure things. And suddenly the bleaching event was global, essentially, like huge tracts of the tropical oceans had their reefs bleach. So they called it the first big global bleaching event. Now, since then, there have been two other El Ninos, and two other big ones, one in 2010 and the other in 2014, 2017. And you got, other global events. If you imagine temperatures slowly rising, it'll hit a certain point where it's reaching a threshold that causes bleaching to occur, right? So it's sort of, you've got the steady rise, but superimposed on that, you've got the El Nino. It's either helping the warming or it's suppressing the warming. In 1998, the El Nino made a big warming that superimposed on the global, on the slow global warming, made a large part of the Pacific get too hot. And it was a mass extinction of, a mass death of coral. Then it cooled down. And so for a while, there wasn't any because El Nino wasn't helping the warming. Then in 2010, it's a relatively small El Nino, but it pushed the temperature again over this threshold value. And there's a second global bleaching event. Then it switches to La Nina, it cools down, the bleaching stops. Then you had an event in 2014 that was like a 3-year El Nino, 2014, 2017, and that caused the biggest coral bleaching events of all. But the point is that 20, 30 years from now, just the background warming of the ocean would make that temperature, that threshold, exceeded all of the time. In other words, it won't be that long before the ocean doesn't need any help to kill the corals. It's going to be warm all of the time, and it's going to be causing these bleaching events all of the time, right? So we went from having tiny localized El Ninos to having regional El Ninos to having global El Ninos. The third big bleaching event was bigger than the first. And in another 20, 30 years, it's hard to see how you can avoid the wiping out of coral reef ecosystems. And this is like a biological holocaust, right? You're talking about families, species, gigantic trunks of the tree of life being lopped off. A huge fraction of fish, I think it's something like half or 30% of all fish spend time in a coral reef, like a creche or a nursery. 500 million people's livelihoods depends on these coral reefs. For me, I mean, some of my colleagues say, well, maybe the corals can adapt quick enough that some of them will survive. But just looking at the physics of what's happening, so it's very hard to imagine how many of them can survive.
It's coming back to Greenland. I was reading that there was rain on Greenland's highest summit, I think, for the first time in history. Right. And if you're looking at this graph here, you're moving into catastrophic areas of extinction. You're talking about in terms of sort of climate events, catastrophic events happening consistently.
Right. If you look back on this, say you look back on this as a geologist, 100,000 years from now, you're looking at it and go, wow, sometime around 2020, a large fraction of all corals went extinct and the entire coral reef ecosystem collapsed. A lot of the fishes went extinct. Like this massive extinction event. But what we see is it wasn't really just one event. There was this cycle helping or hindering the warming. And so there were pulses. So for a long time, these cycles, for thousands of years, these cycles did nothing because the ocean was too cold. Suddenly you get close to the threshold of bleaching and the cycles can make it happen or not make it happen. And then you get to the point where it'll happen all of the time. So it's sort of a wobble and tip. It doesn't just tip in one time. When you zoom in and look, as we can, because we're here now watching it, we see the system wobbling and then it will tip permanently.
Okay, so this is the tipping point that we're talking about. This is your definition of tipping points.
Yeah, this is a tipping point for coral reefs.
Yeah. Okay. I'd love to get questions. I'm really, really grateful. I think the detail that we've gone into is necessary here, and it's been really revealing. Please do start putting your questions in the Q&A box. Michael, I'm just going to come to you personally, because also this is about, I'm going to be serious. This global warming is going to affect our lives, is affecting our lives. I'm sitting here with a fire warming this room. Maybe I shouldn't be. We've got oil central heating in this house, and the question in the back of my head that we don't have the heating on. We try not to because it's very expensive. But the question in the back of my mind is, what do I do? What do we do to move to a more efficient system? These are all questions we're addressing. And it does seem that the world has begun to make a shift, certainly, the advanced world, and to looking at other technologies, whether it's getting, diesel, petrol, carbon burning, cars off the road. And the initial projections for global warming have been adjusted as a result of that. What were you expecting or hoping for from COP26? That's the first question. And then I've got a question about what you are doing personally in your life to prepare for the changes that are coming ahead. So let's look at COP26 first, and the expectations you had from that, And then let's just look at what you're doing in your own life.
Well, my hope is that governments will get serious about reducing carbon emissions in a much bigger way and much quicker, because you can look at the kind of scenarios like, if we just stop tomorrow, or we cut it in 3/4, we keep it the same, we actually increase, and you can look at the consequences, right? And so it's pretty clear now, I think, to nearly all scientists, if we don't have a dramatic reduction in CO2 emissions in 10 to 15 years, there are going to be terrible consequences for people, for nature, for the economy. It used to be that politicians would say, well, we have to choose between saving our climate system and saving our economy. I think people are realizing now for the first time that is not true, that the biggest risk to the economy is climate change. It can make COVID look like a walk in the park, right? And that it can do things that will last hundreds of years. Look at what's happening in California. It's burning, right? Every year we're seeing more and more wildfires. We're seeing more and more droughts. We're seeing the beginning of regional collapse of agriculture. We'll see mass migrations of people, climate refugees, right? I mean, look at all the angst there is in Europe about people coming into Europe, right? And the similar angst in the United States about people crossing the southern border. So everyone's very worried about 100,000 people trying to cross into the United States. But if agriculture fails right through Middle America, right through the big parts of South America too, hundreds of millions of people are going to want to leave. I mean, what alternative will they have? Hundreds of millions of people will have to leave parts of India because they will become unlivable. Very large numbers of people will have to leave Africa because they'll become unlivable, right? The consequences are gigantic and they're extremely negative. So the governments have got to step up and realize the cost of not doing this is much worse than the cost of doing it.
Yeah, okay. We've got a question from Andy Mendes. Warning, Andy is quite good at pinning things on people. Andy, I think you're pinning the the behavior of the US political class entirely on Michael Bevis here, but go ahead with your question.
Mm-hmm. Yeah, usually in these questions, I'm the one that's asking the climate question when Nicholas is trying very hard to do politics. So I'm switching it around this time. I mean, you've just made very clear and straightforward statements based on scientific evidence of the chaos and the disaster we're heading for. So there you are sitting in Ohio State. Why is it that, if we believe it from this side of the pond, that half of America and the entire Republican Party thinks that you're just lying or completely irrelevant? What are you doing wrong is the pinning bit. Why
I can answer that question for you if you want, Michael. I can talk about the US political system in depth and gerrymandering and how Ohio state politics works. We actually come to Ohio every 4 years to look at your politics.
Right, and basically brainwashing, right? So that you've also got huge numbers of people that think that it's a bad idea to take vaccines, right? It's almost unimaginably stupid. And the same with climate change. There are still people denying it. I mean,
why do you? I mean, I guess Andy's question, to take up Andy's question, is why? I mean, there you are. You've got influence around the world. You've people have written around you throughout the world. Why does politicians in the state house have no time to listen to you?
It's basically all about money, right? It's about the special interests of the fossil fuel industry. So they buy politicians. And in the US, for example, basically the Congress and the Supreme Court between them have legalized the bribery of Congress, so that there's huge amounts of dark money going into all political offices. And they tell people, okay, let's stop this shift towards clean energy. Let's support fossil fuels. And there's gigantic propaganda machines pouring out untruths all of the time. So there's a very large number of people that just believe this. And I think the tendency towards political tribalism now in the US is that, if you believe vaccines are bad, you also believe that global warming is not a problem. right? You're actually grabbing whole sets of beliefs because that's what your tribe believes. And this is all being driven by special interests. The hope is that other big companies now are waking up to the fact that the fossil fuel industry, pursuing its own narrow interests, can destroy the wider economy. I mean, the economy is much bigger than fossil fuels, right? I mean, there's a huge economy, the entire global economy, business, manufacturing, industry, satellites, services. It's a gigantic economy. The fossil fuels part of the economy is a relatively small part. And yet, all of the industries, all of these businesses have been watching the fossil fuel companies corrupt the system morally to not fight climate change when it's a horrible danger for future generations, for nature, for our economy, right? So what I'm hoping is that that our corporations are going to wake up and say, well, wait a second, if you support the fossil fuel industry doing this, we're going to start funding other politicians that oppose what you're doing, right? That it has to be money in the solution. The politicians here respond to money, right? And so
Michael,
money
you weren't always in Ohio. You were at Cornell before that at one point, and before that, tell us where you grew up and how you got there.
Yeah, I grew up in Cornwall, in England, and so then I went to Birmingham University where I studied physics, and I went to the US to go to grad school in physics and later in geophysics. So I've lived in I lived in England until I was 21, basically, and then I've lived here, and I've basically worked all over the world. I've worked in, I don't know, 40, 50 countries probably at this point. So I'm very well traveled. I mean, it's a very interesting career. And I sort of see certain patterns. I am distressed by what's happening to American politics. I mean, it's horrible to be here and watch it.
Yeah. Michael, what changes are you making in your own life, and what are you actually doing on terms of what choices have you made in terms of, if you're thinking about carbon emissions? And I know we're talking, it's one thing to about what governments be doing, what the political class should be doing, but what have you done and what are you preparing for?
Well, professionally, I started a big class at OSU on climate change. It's called Climate Change Mechanisms, Impacts, and Mitigation. And it's co-taught with a biologist who talks about the biological impacts of climate change and a historian who talks about, the role of history, what happened in the past when there were climate shifts. So I'm trying to educate something like 140, 150 students every year in climate change so that when they go out and vote, that they will act rationally, right? In my private life, I'm building my retirement home in upstate New York. I'm going there because it won't run out of water, like a large chunk of the country is going to. And I've built a house that's so strongly insulated you can heat it with a candle. And I also my wife and I bought into a community solar farm. So we don't have the solar panels on our property, but we have them in a nearby land. And then we because New York is very progressive, they enable you to basically sell that electricity to the power company, who then give you a credit that never expires. And so we are consuming something, we are producing something like 3/4 of our own energy, right, for that house. I have a fuel efficient vehicle, and my next vehicle will be electric. Right. So I am consciously trying to, lower my own carbon footprint, and so is my wife.
Okay. And what are you continue to study Greenland at the moment? Where else are you looking at? Are you using the same technology elsewhere?
I'm working in Bolivia and other parts of South America. I'm looking at Patagonia right now, looking at loss of ice there. In Bolivia, I'm sort of watching the process of desertification and the imminent loss of water resources. So, I mean, you have two sort of interesting consequences of global warming, which are jointly known as intensification of the water cycle. So as it gets warmer, it causes both more rainfall and more drought. The more rainfall is caused by increased absolute levels of humidity. That is, the air can hold more water vapor when it's warmer. So if it is in contact with the sea for a long enough period of time, and it fully loads its tank, it comes in with huge amounts of water vapor. That's what can make that, like the floods that happened in Germany, right? All these gigantic floods that we're seeing. It also makes the hurricanes more violent because water vapor is energy for storm systems. On the other hand, if the air mass is not in contact with the ocean, if it's been over land for a long, long time, the fuel tank's bigger, it can hold more water vapor, but it's not there. So the fuel tank's empty. This increases evaporative demand because the air always wants to carry the full load. And if it can't have it, it starts to suck it out of anything nearby. It'll suck it out of leaves, it'll suck it out of the soil. And that's why we're getting droughts, and that's why we're getting fires. So ironically, the warming of the air causes both the extreme rainfall, the extreme storms and floods, and desertification, droughts, and wildfires.
That's really well explained. That's great. Thank you very much for that. That's very good. Andy, you recommended a book, Peter Wadham, A Farewell to Ice. Just give us a brief summary of that.
Oh God, I was recommended it a few years ago in a talk at the university, or by somebody at a talk at the university. And it's the first time I understood the sort of the self-generating effects that the professor talked about earlier, where things like the darkening of the ocean and the dirtying of the ice and the removal of the ice actually creates more warming. So you have a vicious circle, as it were. And he bases his book on, I don't know, 40, 50 years of work in the Arctic. And it was truly dismal. I mean, he had no, the last chapter, there's sometimes, but chaps, it'll be fine. There was no last chapter. It was within a mess, and we're getting further and further into a mess. And when you start releasing methane from the permafrost and all the rest of it, then it just it extends. Well, I had two questions, if I may, quick ones, and then I'll go away. But the first thing, a few months ago, Nicholas, we actually had a very positive talk on carbon capture, and I'd be interested in the views as to whether that is scalable to be of any use. But the second question, you talked a lot about the unimaginable amounts of water being released from the ice caps. When will we start seeing that effect in sea levels in places like London, let alone Jakarta and the cities?
Great questions. Please, and also, please, let's have more follow-up questions, please, from other people. Q&A. We've just had one from Andy. Let's not leave it just to Andy and me. Please do put your questions in there. If you don't ask your questions, we have to let our guests go, and the show ends quickly. So please do put your questions there and now. Great questions from Andy Mendes. Go ahead, Michael. First of all, with the impacts of the things you've been talking about, notably with sea level rises.
So sea level has been rising now at about 3 millimeters per year. And that's sort of on average. Now, there are some places where it rises faster because the ground actually is going down. So what really matters is relative sea level, the sea level relative to the ground. So if the ground's moving down, as it is, for example, along the Gulf Coast of the United States, it's subsiding, and sea level is going up, then the relative sea level rise is even larger. So that's accelerating. And how much it accelerates depends on what we do next with CO2, right? Whether we cut it or we don't. I think people sort of think, well, is it about inundation? Not really. If you think about Florida, for example, Miami, the real threat is storm surges. So you get these big surges in sea level due to a storm, and the issue is surge from what level? So as the sea level rises, the surge is sitting on higher and higher starting point. So it might well be, for example, that 20 years ago, a seawall could stop a hurricane storm surge. But the 20 years of sea level rise means that next storm surge will go over the top, right? And so I think that's what's going to happen is we will see large numbers of cities in the Atlantic coastal plain and in the Gulf Coast being damaged by incursions of sea, but it'll be this combination of sea level rise and storm surge rather than some slow inundation by sea level rise. And I think we'll see this, and we'll see similar effects in London. And Bangladesh probably has got like the worst risk of all, right? Because it's so low, so flat, so many people, and it's poor, right? So, but there's going to be problems with flooding events over a significant fraction of our coastlines.
Incredible. I mean, do you look at London at all? My mother's got a question here. She listens in. And her house is actually, when the River Thames reached high watermark, parts of her house I know are below the high watermark. So what are we talking about? Do you look at London?
I haven't looked at it recently, but I know that there are significant parts of London that are not that high above the river level. And so, yeah, there's definitely a risk. I mean, I would personally feel, it's better in a way because than being in Florida or being in the Gulf Coast, because you're not exposed to hurricanes like they are, right? I mean, these guys are basically going to start playing an endless game of Russian roulette in hurricane season. The gun just never gets empty. In London, you can get these extreme storms, but they're relatively rare. So, but I would be nervous if I was within 2 meters of sea level. I would prefer to be 10 meters above sea level. Yeah. It's that combination of the storm plus the base level that's the worrying, not the very, very slow rise of the base level.
Carbon capture, Andy mentioned the program we had earlier. What do you know about carbon capture? Does that give you much confidence? I
do watch it, and I have some friends in the climate change community that feel eventually it will just be necessary to do carbon capture to get the full benefits, right? That we just can't get it down fast enough. So at some point we need to stop issuing CO2 and also get some out of the air by carbon capture. Most of the big technologies, demonstration ones, have been massive failures. Like, there was one plant that they spent $2 billion on, and it never really worked. I think carbon, that doesn't mean that it won't ever work, but it's not working very well now. Yeah. For me, the most positive thing I've seen about carbon capture is actually regenerative agriculture, which is putting CO2 into the soil, which is interesting because it's both a mitigation in the sense that you're withdrawing CO2 from the air and storing it in the soil, but it's also an adaptation, because when you have more organic matter in the soil, it makes the soil healthier and makes it better ability to absorb and retain water. So it's less subject to flash droughts, for example. So that's one I'm sure would work.
Can you give us an example of a project? I mean, I sort of get what you mean, but on a scale, I'm just trying to understand.
Yeah, the regenerative agriculture. There's a movie that's called Kiss the Ground that you can see on Netflix or on YouTube, and it describes it very well. There's also a book called Growing a Revolution that's about the same idea. It's really about getting away from agrochemical farming, where you basically kill everything that's alive in that soil, have it as a kind of a neutral substrate, and then you have to do chemical inputs to grow plants, right? So this is about actually not using large amounts of chemicals, not doing plowing, going back to crop circulation, and also using green mulch, which is like let the plants stay on the ground, cover crops, and let them rot as a source of organic material. So there's like 3 or 4, sometimes 5 components to regenerative agriculture. It's a big movement. It's a bottom-up movement. It's not something that the governments push very much, because the agribusiness industry doesn't like it, obviously, since you're not relying on their products. But it is happening in the US, it's happening in South America, it's happening in Africa. If you watch those movies, you'll get a sense of what it is. It's a big deal, and it could help sequester carbon into the soil.
Okay, we've got lots of good questions now. I mean, some of these are political, and I don't think Mike will be able to answer them necessarily, but let's see what we get. Let's just start actually down under. Let's go to Lewis Towart in Sydney. Go ahead, Lewis.
Hello. I have to confess, I was a trainee greenie back in the 70s at a place you may have heard of, Murdoch University. Oh, yeah. So you're preaching to the converted. We're seeing much more nuances in Australia. Yes, we get storm surges, But that tends to impact upon rich people with oceanfront properties who have very little sympathy from the general mainstream. What we're now seeing as Australia, particularly regarding new coal mines, is the impact of finance. Now, politicians can approve a mine, we can lobby for it, but if the financial markets say we're not going to lend to it, it's very difficult to get it up and running. So we're actually seeing, it's a bit like that comment, oh, my next life, I want to come back as the bond market, everybody's frightened of me. The power of finance to actually do a lot more than politicians.
Right. No, that's a good point. And I actually have been watching this. I've been watching the finance of renewable energy versus fossil fuels. And I think, you know, in the US, for example, no major bank will lend money to a coal company because they understand climate change is going to get worse, right? I mean, anyone can deny the laws of physics, but nobody can change them. And so it will get worse. And so the political pressures against fossil fuels are going to increase. The other factor is that coal is no longer the cheapest energy source. Solar and wind are in many areas cheaper, and solar in particular is often a lot cheaper than coal. So their day is sort of done. I think the fossil fuel industry that will die first in most areas is coal. I mean, it's more or less dead in England, right? It's more or less over now. So that the country which began the Industrial Revolution and which had 1.25 million coal miners at the end of the First World War has basically weaned itself off of coal. And in the US, the number of jobs in coal, for example, is minuscule.
Well, let's bring in Hilary Matthews here, because Hilary spent time in the States and has got a good question here about one US senator who seems particularly wedded to coal. Go ahead, Hilary.
I've just been reading and hearing about this one Democratic senator. I think his name is Manchin, but he comes from West Virginia, which is a coal-producing state, and Biden is on such a knife edge with a tiny, tiny, tiny majority that he risks coming to COP26 with almost nothing because of one Democrat. And it really is very alarming to me that if the Americans can't take the lead at COP26, what hope do we have for Brazil and China and Russia and India?
And Boris Johnson has already said that they're not going to get the sort of the main goals through, are they? I mean, that he's just given that warning already. And
as just as a quick aside for what you were saying is that our dear leader wants to have a new coal mine open, I believe in the Lake District, and possibly open up a new oil wells in the North Sea. I mean, it's really quite depressing. It's nice to hear that there's some good news with renewables coming up, but I fear for what's going to happen with Biden unable to bring a really significant package with him next week.
Yeah, mostly in this country, it's Republicans that sort of aid the fossil fuel industry, but it's not exclusively Republicans. Yeah. And Joe Manchin is a really good example of a Democrat that supports the fossil fuel industries because West Virginia, you know, has been big coal country for a very long time. It actually employs very few people, which is what it's sort of part of their culture, but it doesn't really employ very many people. And it's poisoned many of their rivers, this mountaintop removal where they blast off the top of a mountain and they dump all the waste into the valley between the mountains. So you've got all kinds of cancers in fish, cancers in birds, cancers in people. I mean, it's nightmarish what's been happening in West Virginia for decades. So it sort of reminds me of when I was a boy in Cornwall, everyone were proud of the tradition of Cornish tin and copper mining. But if you actually go back and read what it was like to be a tin or a copper miner, it was horrific, right? This boom and bust, being laid off, starvations, bread riots, police coming in, the army coming in. It's horrible. So, and same in West Virginia. Now it's a very hilly, sort of small mountain state with most of the towns in river valleys, and they are wide open to flooding. So this is not in the interests of the people of West Virginia. It's not in the economic interests of the state, right? This is in the interests of big coal. And Joe Manchin is pursuing the interests of big coal, not the interests of the people in his own state. This is what it's all about, right? Is that politicians are being driven by money from the fossil fuel industry, and that's why they're doing what they're doing.
Can I just quickly add there that I've seen this? Nicholas said that I've spent time in the States. I lived in Alaska for 20 years. And so I've seen the oil pipeline, the North Slope. I've actually been up there. Mm-hmm. And I've also seen firsthand what is happening to the glaciers in Alaska, the receding glaciers and the permafrost disappearing. And yet the state of Alaska is absolutely, the political system there is absolutely determined that we want more oil on the North Slope. And it is very, very political. And it's a battle that it seems unwinnable, and you can see it. It's right there for them to see what's happening to the glaciers, but they just think, oh, it's a cycle, it's a natural cycle, it'll all get better.
Yeah, I mean, people say that. I mean, I doubt that many people actually believe it. You know, you get guys like, you know, Ted Cruz, Senator Cruz, who sort of just flat out denies that climate change is real, right? Now, this guy went to Harvard and Princeton. He's got to be a pretty smart guy, right? So I often quote some of the things that he said in my class, and I asked the class to vote. Who thinks this guy actually believes what he's saying? And like almost always, like 90% of the class don't believe that he actually believes what he's saying, right? And does he have a moral responsibility to say what's true when the consequences for future generations on our economy are so awful? Well, I think he does, right? I mean, this is sort of a variation on the tragedy of the commons, right? The tragedy of the commons is where you have a shared resource and everyone overexploits it to the point that they destroy it. And in this case, the resource is our environment, you know, the fact that we live in this place and we have nature giving us services. Everyone knows that we are destroying this common resource, but they want somebody else to fix it. Right, and that is a real tragedy. The new element of this is that whereas the classic tragedy of the commons is people destroying their own well-being, and in this case, we're destroying the well-being of future generations, not just our own.
I think it's much more libertarian than that. I think it's people believing that they shouldn't have it. It's an American thing to some degree, but I think it's some other. In Western states, why should the government tell me what to do? Why should you interfere with my freedom to do what I want? Whether that's driving a car, burning oil, flying off on holiday. These are my rights. This is who are you to tell me what to do? And that determines your overview on the environment. Anyway.
Yeah, it's true. But on the other hand, people accept that they're not allowed to drive a car while they're drunk, right? Because that's not in the interest of society. So there are many examples like that where people accept that the state needs to pursue the common good, and that limits your individual freedoms. But in other cases, they are all for the individual freedoms, even though they're destroying the futures of their own children and grandchildren.
Yeah, no, I get it. It's arguable, I guess. It's easier. It's more nebulous for them to contest it. Let's get in. I've got one last question. Let's take Sarah Biffin and ask about. It's really asking the same question again, but it's a good one nevertheless. Go ahead.
I wondered if you can put any date on when populations would have to shift from where they're living now if not enough is done, and when agriculture will start to fail, also shifting populations. I
think you were saying it's already happening.
Yeah, it's already happening. So, I mean, for example, California now is starting to ration water, which is, that's been very, very rare. But we're watching the steady desertification. There are other places, for example, like Kansas, where they have been able to do agriculture because they are pumping water out of the giant aquifer called the Ogallala Aquifer. That aquifer is now virtually empty. So it has 100,000-year recharge time. It won't fill up anytime soon, and the whole area is drying. So it's hard to see how you continue to do agriculture here for more than 10 or 20 years, right? It's just going to get too dry. Back in 1950, when Roger Revelle was warning about global warming, one of the things he said is West Texas will turn into a real desert, right? So we're going to watch this desertification just wipe out agriculture in certain areas, and it's already started. So that there are places in Chile where the agriculture is failing. There's places in the Central America region where it's failing. There are places in Africa where you've got aridification, desertification, the Sahel, right? People are trying to adopt the kind of crops to stave it off, but every time you increase the air temperature by 1 degree centigrade, the carrying capacity of water vapor goes up 7%. So 2 degrees, 14%, right? And when that expanding tank is not full, it sucks that water out, right?
Say that again, just repeat that again. So each for half a degree of temperature increase, say it again.
1 degree. 1 degree. The carrying capacity of the air for water vapor, the size of the water vapor fuel tank, goes up 7% for each 1 degree. Now, when that tank's full, you've got giant rainfalls, giant hurricanes, and you got floods. And when that big tank is empty, you got drought and wildfire and agricultural failure. So there's absolutely no way that the situation is not going to get worse if it keeps getting warmer. Right? There's no way. It's just basic physics. That physics, by the way, has been known for like 150 years. So it's just really basic physics. So it's already started and it's going to get worse. How much worse, how quickly, depends on what we do. But I think we're going to see mass migrations unlike anything we've seen in history within 15 years.
My thanks to Professor Michael Bevis. It's been a very informative, albeit depressing hour, but one which has obviously been very, very well informed. Thank you so much.